Look.
All right, guys, so let me say good morning to everyone, and let's probably start. So thanks for joining this lecture. Hopefully you're doing good. And well, being honest, we are supposed to have about 7 lectures at the first module, and actually this one is the 4th one. So we are in the middle of the topics that we are keen to get into. And so let's carry on. Hopefully you enjoy your classes and you had practiced some of the probability distribution functions and you train some of the skills in terms of probability theory and statistics. And we may keep working to, well, to develop them. All right, so today I'd like to talk about the conditional probability distribution, the conditional probability definition, and basically about its application. So hopefully we are going to introduce today the metrics that are called covariance and correlation. Well, I may suppose that you have heard already the concept of correlation or covariance. Well, because you're those who are going to be the experts in data science area. And these two metrics, covariance and correlation as well, they are the basic in order to define how strong the association of two or more variables is. But we will introduce all of that. To recap, we finalized the last lecture with the definition of the conditional probability, and we said the following. Look, the basic definition of the marginal probability, those probabilities that you used to sorry, that you used to define might be called as oh my damn Lord. So the previous that's not fun. What's going on? Very sorry, guys. Now it seems to be better. All right, so I was about to say that PB, the probability of the random event, well, it should be called a marginal probability to be sure, but we never say marginal. We usually say sure, just the probability. The conditional probability is sort of instrument that helps you to re-estimate the likelihood of any event, given that you know some extra information. So basically, you know that some condition has happened, and this gives you some extra insight and information about the about your main random event. So we said a probability of a random event A, given that we know that B happened, equals to the fraction of the probability that both of these happens, defined by the probability of condition. And actually, that's a pretty smart idea, because look, here's the event A, here's event B, and someone told you that event B has happened. So the only option to observe that random event A happens as well is basically to be at this area that is crossed with the dark blue lines. All right, and then what you do, you say, if all the points inside this red circle are sort of uniform, but basically if they are equal, if they are identical, the probability to be inside the area that is crossed with the blue lines, given that I am inside the red circle, is basically a fraction of their areas. And we said that the probability concept might be treated as sort of area in terms of Wien's diagram. So that might be applied. Right now, we say that the probability of A given B equals to probability of their intersection divided by the probability of B. And just to play with this formula, I may say the following example. For example, I just took it from the UL exam. And here is a very basic formula, a very basic problem. So say you read a newspaper with the probability 40%, all right? You say you drink coffee with a probability, say 70%. And you basically read and drink coffee simultaneously with the probability 20%. And now is the question. If I randomly pick someone and I know that he or she just read some newspaper, so this information was given to me, what is the probability that he was drinking coffee at the same time? And well, then we say that it is a probability of coffee drinking intersected with the newspaper reading. So basically these two events should be done simultaneously, divided by the probability of the condition, basically the newspaper reading. In our case, it gives us 0.2 divided by 0.4, so it's 1/2. And now I know that someone drinks coffee with the probability 1/2 if I was told that he or she was reading before. So this is the concept of conditional probability. What we should definitely think about is actually the allocation of two random events. Here's the idea. Look, we have two cases when when your event A is interacted with the event B. Well, the first picture on the left side of your screen shows that there is no intersection of these two random events. And actually, because of that, you may say for sure that it is impossible both of these events happen simultaneously. Well, actually, you know from the first picture, from this one, that once A happened, B cannot happen simultaneously, and the vice versa. Well, as a result, the conditional probability is not applicable here, simply because there is no intersection area of these two random events. And here's an alternative one. If your condition is fully inside your main event, then let's analyze what P A given B will give you. Well, now let's think about that. We know that B happened, all right? So we are in the middle of this circle somewhere. What is the probability that A happened? Well, obviously, this is the probability of B to happen because because B was fully inside of A. And actually, this is the reason why conditional probability is not applicable as well. Well, although it might be applied here, but it's useless because, well, you know, if B happened, then A happened obviously. And these two kind of corner solutions, well, hopefully you know what corner solutions means. By saying corner solutions, I mean that these are two extremely different cases at this problem, all right? Well, hopefully it makes sense. And we are not dedicated to analyze these two cases, but we are going to analyze somewhere in the middle. When you have two events, they do intersect somewhere, and then from capturing some information, we are going to increase the accuracy of our evaluations, of our probability estimations. Here's a chain formula. Well, obviously, from the definition of the conditional probability, that you're totally right. Yes. Thank you very much. Yeah, it's a Saturday morning, and I haven't had my cup of coffee, but you are very smart, guys. Isa, Adam, thank you very much. If you're totally right, should be 1. That's bright. All right. So now it makes fully clear. Let's move on. The chain formula. The chain rule formula is actually, well, it's obviously straightforwardly developed from the conditional probability. And what it says that given you know the conditional probability, you may develop a formula to estimate the probability of the intersection of two events. And now we say that P of A intersect B is actually equal to the conditional probability of A given B multiplied by the probability of condition. So that's nice. Now you may be able to estimate these probabilities. But now is the idea. What if your set A is split into some areas that were presented by the intersection with some conditions, all right? Imagine a story when your random event A is intersected with a list of other events. Given that we know the conditional probability of A event, given all of the conditions, we may be able to apply this chain rule formula in order to capture the probability of every intersection. And actually, this moves us to the formula that is called this total probability formula, but this is just a partial case. So here's a story. Here's your event A, here's your event B, and outside we have a B complement. So we may say that this is actually A intersect B, and then this vertical line crossed event might be interpreted as A intersected B complement. And then what you say, you say that PA is actually probability of A intersected B plus probability of A intersected B complement. And once you apply the chain rule formula to both of these intersections, you'll get this formula. I would not like you to concentrate on the total probability formula, but I'd like to move on in order to introduce the extension of that formula. It is called as a full probability formula. So what we are seeing right now is a partial case, but still we are going to introduce a more extensive one. Before we do that, let's play a very basic problem. All right, so this problem was taken from the section A of the UL exam.
Could you show the formula again, please?
Yeah, you're welcome.
Thank you.
Good. Now let's practice it. And here's a problem. So I took this problem from the UL examination. Hopefully it was 2006 or 2008, I guess. So we have two machines, all right? And they are producing some details, some stuff. And we know that the first machine is producing 60% of total turnover. And it has such a setups that the probability of a defective detail is about 3%. How's about second machine? Well, it is producing 40% of turnover, and the probability of defects is about 5%. All right. Then you have a box with all of the details produced, and you do not know which one was done by a precise machine. So you pick a detail on random, and now we want to evaluate the probability that a randomly picked detail is going to be defected. Well, we know that these events may be split by two. Well, the first, be defected and be produced by the first machine. So this is the first simultaneous pair, plus a probability of a defected detail that was produced by second machine. And actually, I am intersecting these two events because I wanna they both happen simultaneously. If I did not care about them happening simultaneously, and if I was wishing to get at least one of two, then I was doing the union. Then I would do the union. But here, I'd like to guarantee that both of them are happening simultaneously, and that's the reason why I'm trying to estimate the probability of the intersection. And then we apply a formula that is called the full probability formula, or that we presented a slide ago by saying the total probability formula. So here I say probability of being defected, given that I was producing by the first machine times the probability of being produced by the first machine. And here is the same application multiplied by the condition. Then we know probability to be defected, given that it was produced by the first machine, so it's 3%, times the probability of being produced by the first machine, so it's 0.6, plus 0.05 times 0.4. And here the most complicated part starts. So it's what? It's 3 times 6 is 18. And we have to cross 2 over, so it's 0.018 plus 0.02. And so it's 0.38. it is slightly less than 4%, the probability of the defected detail is slightly less than 4% chance. And voila. So here we applied a very nice formula to evaluate the probability of the event that just one randomly picked detail appears to be defective. And we succeeded to do that because we were able to split all of the events into a combination of intersections. All right. Just a hint. Because, well, frankly speaking, you're going to be proposed to solve slightly more complicated problems where you may have a number of various intersections, conditions, and the problem might be slightly extensive, and it would be good to have a very nice way to visualize what is given. In order to visualize the problem set that is given to you, I would like you to propose you apply the concept of probability tree. The idea about that is the following. You're drawing a tree starting from the very beginning in order to visualize all of the events and parts that are happening at the problem. So let me structure the previous problem that was related to the defect machines with the probability tree concept. So here is a randomly picked detail. The first, what I visualize is actually what machine were producing this detail. I have two options, and I have two options, and that's why I'm writing two edges. And here I may write first machine and second machine. Then each of these machines may produce defected and not defected detail. Defected and the not defected detail. And if I need, I may write the probabilities of every of these of every of these edges. So here were 60%, here 40, here we have 3%, here 97, here 0.5%, and here 95%. And if you need to evaluate the probability that second machine produced a non-defective detail, then what you do, you basically multiply these probabilities. And this is going to be a probability that second machine produced a non-defective detail. So this is not rocket science. It's just a very nice way to present the problem, just for you to visualize what the what the problem is about. For example, if we speak about the toss, a coin tossing problem, I may say the following. Look, let's say that you toss a coin 3 times. All right, so 3 times tossing coin. Here's the first, head and tail. Here's the second round, head and tail. And here's the last one. Head, tail, head, tail, head, tail, head, and tail. So here you have double head and tail, head, double tail, double head, tail, double tail, triple tail. And this helps you to explain, to visualize, to play with some scenarios where you want to capture, say, for example, you'd like to evaluate the probability of event where you have at least 2 tails. Well, at least 2 tails, what outcomes are fine to you? This one and these 3. So then what you do, you evaluate these probabilities and you sum them because they are independent, because they are outcomes of the same experiment. All right. So just to recap, this nice way to visualize a problem, and that's it. All right, let's move on. So going back to the full probability formula that we just practiced within one problem set, I would like to generalize it up to the multi-dimensional case. And here I say that this rectangular is actually population that may be split by a finite list of events B that have empty intersection, but their union, their total union, gives you the full population or sample space. All right, so we used to call these events as collectively exhaustive. So they have empty intersection, but their union gives a full probability set. Good. Let's say that here I have B1, and I have B2, and I have B3, and here I have B4. So we say that we may split the population into a list of non-intersected sub-events. And then someone tell you that there is an event A, and here I presented it with with the red color. So what I know here is actually the following. The event A intersects with all of these sub-events B. And if someone asks me to evaluate the probability of A, then I say, look, according to the total probability formula that we just discussed, it's going to be A intersected B1, A intersected B2, A intersected B3, plus A intersected B4. And this could be done up to the sub-event B subindex N that illustrates that we have split these population into a list of the collectively exhaustive events B. Once you apply the chain rule formula to every of these probabilities, I mean to the intersections, you'll get what is called a full probability formula. So sometimes we say total probability formula, but your study guides and your books, you're going to be sent by the London School of Economics. They call this formula as a full probability formula, so be fine to apply all of them. What it says that if you know the probability of the conditional probability of event A, given that your conditions happens, plus you know the marginal probabilities of every of these conditions, then you may evaluate the probability of your event A. And actually, this was the method that we applied in order to solve this problem. But here I had 2 options. So basically, 2 machines could be operating the details instead of many of them. So if I have n machines that are producing the same equipment, then the full probability formula is fine to be applied. That's it. Now, we know the way how a probability of random event may be estimated. All right. So we are fine to evaluate it. Now, what I'd like to develop is actually the following application. All right. So here on the top, you know how to evaluate the probability of A, and you know that PA intersected B is A of a given B is the probability of their intersection divided by the probability of the condition. Now let's swap. So I swap B and A there. And what it gives me is the probability of B given A is the probability of B intersect A divided by a probability of A. The intersection is a symmetric operation, so B intersected A or A intersect B is actually these similar structures. And now look, what we may do now is that we may implement this formula inside the fraction. If I do that, I'll get PA intersected B divided by PA given B plus PA given B complement times the probability of B complement. All right, so what I did, I just applied the full probability formula that we practiced with with the machines operations and all of that. And what I just did was proposed and presented by Bias. And well, he was a pretty nice guy. He had done quite a lot in mathematics and in statistics as well. And he proposed the following formula that every of the statisticians decided to call as Bias formula. Well, if you ask me about the application of this formula, well, I will probably say that this is not a very useful formula, but because it was developed by a genius mathematician, we all know this formula as a Bias formula or a Bias theorem. So if you, well, hopefully you do see both slides on your screen simultaneously. And what I'd like you to mention is that we started with a probability of B given A. What is highly important here is that your main event is A and B is a sort of the condition that you are analyzing. By Bias formula, Bias theorem application or applying, what we do, we try to measure the probability. We try to measure the probability of a condition happening, given that your main event has happened. So basically, what Bias theorem says is, well, it might be interpreted on this example. You know that A has happened. What is the probability that it happened at this area? So that's what we are trying to evaluate with the Bias formula. And then we are applying the definition of the conditional probability straightforward. And then we apply the full probability formula. And the rest, what we could do, we may replace that with P A given B times marginal probability of B. So basically, that is applied here. And if you combine both of these substitutions, you get what is written here. A probability of B given A is a probability of A given B times the probability of B divided by the total formula, by the total probability formula. And that's it. So that gives you the bias theory. Well, if you ask me, is it really useful formula? I wouldn't say yes. If you ask me, should we know this formula in order to pass the UL exam? Being honest, if you do not recall this formula, but given that you understand the intuition and the sense of all of the transformations and operations that we are doing, you will be able to define this formula by yourself. It's pretty intuitive. But if you may learn it for granted by heart, then, well, it might save a couple of minutes you to recall the formula, but that's it. For those of you who are going to be experts at machine learning stories and machine learning models, I'd like to mention the following. So maybe, you heard maybe, the statements like Bayesian classificator or Bayesian estimation. Well, hopefully you heard that. Well, dealing with machine learning and data science, the key part of model calibration is to define the objective function and find such a combination of parameters that minimizes your loss function, or basically that are optimizing your objective function. You either maximize the accuracy or minimize the squared sum of errors. Sometimes you will be doing some probabilistic models or data that are not given for you for sure, and basically they might be interpreted with some probability, under some probability assumption. For example, the classification. Someone gives you a picture and asks you to code the classificator, whether it is a cat or a dog. It's pretty straightforward problem. But in order to make these classificator being accurate, you will apply some techniques, and one of these techniques is actually based with with the Bayesian methodology, because it introduces the probability that the data you are operating might be shifted because of noise. And these noise detection is possible to be done because of the Bayesian classification and Bayesian objective functions. All of what I have said is going to be presented to you at your third year of studies within the machine learning course, and it's going to be based on that formula. So the only moment we're going to be working with this formula is a case when you are going to develop the noise detection machine learning models and working under some of uncertainty. All right, so what I'd like to do, and what I was about to do, I was about to highlight the area of practical application of this theory. I'm not interested to present you the useless theory that is written in the huge books. Well, if you want to do that, I may share with you my library, and you may read all of this stuff. But I'm happy to present you the most useful, the most applied stories that will help you within your machine learning models, etc. Now let's move on. Oh yeah, that's the partial case of Bayesian formula, given that you have only two possible subcases, whether B happened or B complement happened. Well, because hopefully you recall that B and B complement are collectively exhaustive, and this is fine to be applied. If we go back to the problem that we just analyzed, what we did before, we estimated a probability of defect detail, and we got that it is 0.038. Now we may estimate a following question. So here is a question. If I got a defected detail, so basically I was given with a defected detail, all right? So I came to the store, I randomly picked a detail out of the box, and it appears to be defective. The question I have, what is the probability that this randomly picked defected detail was produced by the second machine? All right, so this is a conditional probability. Given that I randomly picked a defected detail, what is the probability that was done by the second machine? Well, and this may be estimated by the Bayesian formula. So it's going to be P second machine intersected with defect divided by the probability of defected detail. Well, I'm happy because we just estimated the probability of being defected. It was 0.6 times 0.03 plus 0.4 times 0.05. And we evaluated it, it is 0.038. I was about the probability of the intersection. So it's actually probability of being defected given being done by the second machine times the probability of the second machine. The probability of being produced by the second machine is 0.4, and the probability of being defected done by the second machine is 0.05. Well, as a result, it gives you 0.020 divided by 0.038. This is a probability 20 over 38. Sorry. Very sorry, guys, about my voice. I have no idea why this happened. So what we estimated is actually probability that given that you captured the defected detail, it was done by the second machine, and it appears to be 20 over 38, slightly greater than 1/2. And yeah, that's not fun. That's not fun because, well, the percentage of being defected is pretty huge. That's not good for the industry, but I'm just kidding. All right, so we applied this formula, we practiced it, and now we may go to the next topic. And the next topic is actually highly important. Well, if you recall the previous problem about the machines and defects, you see that some of the machines, they affect on the probability of defect. All right. So there is some association with the machine and the quality of details produced by it. And look, you may have two random variables. Well, in my case, that's a number of machine that was producing my detail and a number of defected details. Does not matter. Speaking of a pair of random variables, I may guess, for example, a price of oil and the dollar ruble exchange rate, USD ruble exchange rate. So these are two random events. Or for example, a random variable that measures the mood of your lecture, and another variable that quantifies the complexity of the final exam. So these are two random variables as well. Well, obviously, some of the random events may be associated with another. So, you know, there might be an effect of one variable on another. For example, if your lecturer is angry and sad, then obviously the exam is going to be more complicated. For example, if today is going to be raining, then probably tomorrow is going to be raining as well. Well, these variables, they affect each other. And what we'd like to do, we'd like to be able to measure the association of these we'd like to measure the association between these two random variables. And that could be done with metrics that are called covariance and correlation. And we start with the covariance metric. Before I demonstrate the formula, it is defined, I'd like to highlight, and you capture it into your notes on your scratch of paper or your iPads or whatever. That covariance metric may be applied even only if you're supposed to have the linear association. The linear association is measured by the covariance. Well, by saying linear transformation, you hopefully recall your linear algebra classes. Well, hopefully, I hope you enjoyed it. And if you have a random variable x, a linearly transformed variable y may be written as ax plus b. So under assumption that these sort of associations is fine to be applied, the covariance is going to evaluate how strong is their association. All right, good. Now let's think about the way how covariance might be evaluated. Look, the only you know are the probabilities of every elementary outcome, and you know some elementary outcome values, and that's it. So that's all what is given to you. So what you could do, you may run some experiments, then you may compare what results you got. You may write some values. So basically, you may collect the following graph. On the first round, we got x being equal here, then here, somewhere here, here, and here. And y on the and y is going to be presented with red color if you a y variable, sorry, and y to give you that point, then give you this. So what you see is actually the following: x fluctuates like that, and y fluctuates. It's actually, well, the fluctuations of y are very close to what x is doing. All right. So the key moment here is to agree that they are fluctuating very, very similar. And because of this similarity, we may introduce the measure that is actually called a covariance. And what covariance do, it measures the expectation of the multiplication of two of both variables deviating from its own expectation. Deviating from its own expectation. And yep, so what we say is actually, look, we know that random variable x has its expectation. We know that y has its own expectation, and the more they are deviating from their own expectations, it increases it increases the number of simultaneous deviations. On the bottom of this slide, you have a slightly shorter version of these formulas. So covariance may be measured as the expectation of their multiplication minus the multiplication of marginal expectations as well. So both of formulas are identical. And if you want, we may derive the bottom formula. It's not a big deal. It's pretty straightforward way how it is derived. In terms of the discrete random variable, we say that we have probabilities of every elementary outcome, and every elementary outcome is presented by the variable x and by the variable y. And actually, I have a typo. I'm very sorry. Here's a typo. There should be 1 minus the expectation of y. Now let's think about what this metric tells us. Well, actually, this is a very nice metric because, look, it helps you. Yep, Nikita, we are going to speak about covariance for the next 15 minutes, so do not panic about that. What covariance gives us is actually quantity that is designed in order to split the association of 2 random variables by 3 cases. The covariance may be positive, the covariance may be negative, or it may be 0. Let's analyze all of these cases. If it is positive, then obviously x is greater than its own expectation, and y is greater than its own expectation. So basically, it says if the covariance is positive, then once x increases, then y increases as well. If the covariance is negative, then obviously well, basically, let's think how this value could be negative. Well, it could be negative if and only if one of these 2 brackets is negative. So it says that if x decreases, then y should be increasing, or if x increases, then y should be decreasing, right? And what happens if the covariance is negative? Oh, sorry, is 0, is 0. Well, covariance is 0 means that one of these brackets is 0. And ideally, in order to get the full 0 formula, we should say that one of these 2 brackets is always 0. Now, what this does mean? Well, saying covariance is 0, and imagine you have 2 variables. Here's the first, and here's the second. The covariance is a pretty tricky, is a very tricky metric, but quite informative. It says how many covariations both of your variables has. Look, we said variance is a metric of fluctuations of one random variable. And covariance means a cooperative variance. So how they are varying simultaneously in a cooperation. That's why it's called covariance. If it is 0, it means that while one random variable was fluctuating, another was flat. It was fixed, so it was equal to its own expectation. While once the first is not fluctuating, the other was fluctuating a lot. And if two random variables has no periods of time when both of them are fluctuating, then their covariance is 0. Well, that's the way how it is defined. And the only positive story about that is actually that is the following. Covariance helps us to distinguish whether there is a positive association of two variables. The positive means that once one increase, another increase, or if one decrease, the other decrease as well. The negative means that the increase of the first leads the second to decrease, and the decrease of the first pushes the first to increase. On the case where covariance is 0, well, there is no association then of two random variables. And what's fun is that covariance is an unlimited metric. So it might be either minus infinity or plus infinity. And because of the definition of the covariance, it says quantity of their joint fluctuations. We cannot compare two covariances. Well, because look, if you have two pair, a random event x, y, and another random events, random variables x and z, and say you measured covariance of both of them, and say that the covariance of x and z is greater than the covariance of xy. Could we say that x and z has a stronger association than xy compared to? Well, we cannot compare. We cannot compare the association strength because by the covariance. Why? Because it's going to be affected by the variance of z. If z was fluctuating a lot from bottom to the top, then the covariance is going to increase a lot. And because covariance is not a limited value, it is good. All the researchers loves it, but the drawback of this metric is that, as I said, it is unlimited. So given that you have in covariance 10,000 or 20,000, it tells you nothing. The only you can do, you may say that it is positive, and that's it. That's pretty. Just few of statements that we would like to be able to do. And because of these drawback, the derivative metric was another metric was derived, and the other metric is called. Oops, let me show you. Is called a correlation. The second metric is called a correlation, and what correlation says, it actually normalizes the covariance by the square root of variances of both of the random variables. And let's say that I'm trying to evaluate the covariance of x with itself. Well, a covariance of x with itself is a correlation of x with itself is a covariance of x with itself divided by variance of x times the variance of x under the square root of. A covariance of x with itself is a variance by definition. Hopefully you recall this from the last lecture. And if you simplify the denominator, you have variance of x. So here I got +1. If I wanna evaluate a covariance of x with -x, then I get covariance of x with -x, covariance of x times a variance of -x. Minus goes outside. Here I have what I do have there. The multiplicator goes outside and must be squared, so it has 0 effect. Well, if you simplify, then you get -1. And what's lovely about covariance is that it is limited. Well, it's actually, sorry, it is bounded. It is bound by -1 and +1. And these, what I just highlighted on the top of your screen, is actually the best that could be done out of that case. So covariance, correlation is an alternative based with a covariance metric, and the correlation is actually bounded. And now, because of these bounds, we may interpret a value of these metric, of these quantities. So here you may say, the greater covariance is, the more strong is the association of two random variables. The correlation is usually written with the Greek letter rho, but just a way to call these metric. So the greater rho is to +1, the more strong is the positive association. So ideally, if your random variable are identical, then a covariance is +1. And this helps a lot because thanks to that, we may define the cases where both of your variables are linearly associated. To recap, a covariance and the correlation are two metrics that are applied in order to evaluate the quality of association of two random variables. And covariance was the first idea generated at this area of math, but the correlation is sort of modification of covariance that eliminates all of the drawbacks, but helps us to claim whether random variables are positively or negatively associated. And here might be a question: what is the reason to evaluate the association of two random variables? Well, here's the first example. Given that you wanna model some random variable y, and you have very few data set about that. Say you developed a very good model about random variable x, but you failed to do such a nice model related to random variable y. Well, in this case, if you may prove that y is correlated with x, then you may apply a model x in order to define and describe random variable y. It's possible. And sometimes we do that because, well, we wanna be able to replace one variable with another. The other alternative, the other example is that if we know that two or more random variables are correlated a lot, then we may eliminate the useless variables and play with the most important, with the main one. So this is very close to what you used to do at your linear algebra course, where you were trying to estimate the linear dependence or independence of vectors. And if vectors were dependent, then you never included them into the basis, if you recall that. And actually, the same story, absolutely the same story, is going to be done in statistics as well. If we know that two or more random variables are correlated, then we leave the main of them, sort of eigenvector. But it's not fully, it's not the same concept, but the intuition is 100% the same, absolutely. Now let's go back to some of the properties. Well, covariance is a symmetric metric, and covariance of x, y is equal to covariance yx. If any of variables are multiplied by coefficients, then these coefficients may be extracted outside of covariance as a multiplicator. If you are covariating x with a constant, then obviously, because constant has no fluctuations at all, the total covariance is going to be 0. The covariance of x with itself is a variance, as I just told you, but this is pretty easy to be proved. What variance is, it is an expectation of x squared minus a squared value of the expectation, if you recall. And what covariance of xy is, it is an expectation of multiplication of two variables minus the multiplication of two expectations. And if you replace y with x, you get a totally same formula like your variance. So this is pretty straightforward. A highly important moment is actually here, because a variance of the sum of two random variables is a variance of the first plus a variance of the second plus double value covariance xy. So this is a highly important moment because it affects a lot on the evaluations. So let me try to elaborate that. So I'm gonna apply this definition. So it is a variance of square minus a squared value of xy sum. That gives you an expectation of x squared plus 2xy plus y squared minus an expectation of x plus an expectation of y under the sum. Then what I do, I basically split the first expectations into a sum of the expectations. Hopefully you recall that the expectation is a metric that has the linear association, and it's fine. It commutates with the sum. Basically, we have no problem to split it into the sum of expectations plus the expectation of y squared. And then what I'm gonna do, I'm gonna combine these elements. So that minus this give you the first variance, y squared minus y minus the expectation of y, and the expectation squared gives you that, and the double expectation of the multiplication minus the multiplication of expectation gives you the covariance as well, and that's it. So basically, it is proved in a straightforward way. I would recommend you to practice with all of these transformations and extractions and prove the property number 4. It is proved in the same way like I did all of the previous. So what you do, you apply these formula to the sum, you split it accurately, and you recombine them into the following right-hand side. So the covariance of two sums is a sum of covariance of all possible pairs. So basically, u and x, u and y, v and x, v and y, and that gives you the total covariance. So it's pretty linear. All right.
Sorry, may I ask a question?
Yeah, you're welcome.
Could you repeat one more time how we get the formula for covariance in the second line, covariance of x and y, which is equal to expectation of x and y minus double expectation?
All right. So we go back to the definition of the covariance, and we've been said that it is an expectation of these two differences. Then what we do, we may open these brackets, and then we have xy minus expectation of x times y, xy expectation minus x times expectation of y plus expectation of x times expectation of y. So what I did, I just multiplied these elements. Then let's think a little bit about it. We know that x and y are random variables, and the expectation is not a random variable because it is a constant. It is fixed value, and the trick is that the expectation of x is an expectation of x. Because look, you know the probability density formula function.
Yeah, it's clear.
Yeah, hopefully it's clear. And then you split this expectation into a sum of expectations plus the expectation of x times expectation of y. And then let's think.
Yeah, we can cancel the third and the fourth term. And
yeah,
okay.
Yeah,
okay.
Brilliant. That moves outside, and voila. And you got, sorry, and you got this formula. So actually, I would say that you should recall this formula because it's gonna be more convenient and you will definitely practice it much more often instead of this one. It's pretty complicated to be applied. And this as well, this obviously as well. Going back to the correlation, let me write here a note for you, having it here that correlation is covariance divided by a sigma x times a sigma y. And by saying sigma, I mean the standard deviation of the random variable. And the standard deviation, as we used to say, is the square root out of variance of your random variable. All right. All right, good. So what we did, we introduced the concept of covariance and the concept of correlation as well. So this week, you are going to practice with your class teachers to solve some conditional probability formula problems. And you will be trying, you will start to evaluate the covariance and correlation as well. Next week, I'm going to introduce a completely new concept at statistic. But before I'll do that, we will have some minor practice, and then we will discuss some standardized problems on the correlation and covariance as well. So do not panic about that. We are going to have a lot of practice in order to get into all of these tricks. Today, we presented this concept, and next week, we will have some practice about that. Well, let me wish you to enjoy your Saturday, to enjoy your weekend, and wish you to do your best with your studies. Do not hesitate to text me if you have any questions, and enjoy your studies. Thanks for your attention, and see you.
Thank you very much.
Yeah, thank you very much. I have a question.
Yeah, please.
More about organization.
Yep.
Maybe
Thank you.
could
Yep.
do our Telegram chat as open chat, because we cannot write there anything, and the only way to write you is on Outlook, and it's not so convenient, I think, because
Well, I'm not against if you are texting me on the Telegram channel and at the private Telegram chat, as some of your classmates do. So you may see my Telegram nickname. You may text me at the Telegram, but I'd like to have the Telegram channel done in one way in order to have a fully clear information about all the materials, links. So it's kind of a syllabus for you to see all of the material links, homeworks, and slides that are provided to you. But if you want to text me at the Telegram, do not hesitate to do that.
okay.
My nickname was written at the Telegram channel, so that's fine.
Okay.
All right?
Bye.
Yep. Enjoy your weekend.